In this tutorial, we're going to program the logic that's going to allow us to spawn infinitely many forward bridge segments in the scene. So let's jump right in. Go to the scripts folder in your project's asset folder and create a new C# script. Let's give it the name bridge spawner. Now let's create an empty game object from the menu bar and call it bridge manager. Let's reset its transform component to 000. Select the bridge manager game object and select add component from its inspector window. Search the newly created C# script, which is bridge spawner. This is yet a third way of attaching scripts to game objects in Unity. The first one we saw was simply dragging the script onto the intended game object in the game object hierarchy. The second way was dragging the script to the inspector window of the game object. And this is the third and final way of attaching scripts to game objects in Unity. It's useful to know all the different ways of doing something. It makes you feel like you've really mastered the subject. Now open up the bridge spawner script in Visual Studio. The first thing we need to do is put all of our bridge segments prefab in one variable. So let's create a public array of game objects and call it bridge prefabs. An array in C# is a variable that stores a collection of like items. So this bridge prefabs array can only store Unity game objects and nothing else. And we put these brackets after the variable type to indicate that it's an array. Now let's save the changes to our script and go back to the editor. Let's click on the bridge manager game object and go to its inspector window. You can see that it's asking us to declare a size for the array. Let's put in 8 because we have 8 prefabs for our different bridge segments for now. You can see that 8 empty game object fields have been added in the inspector window. And they're numbered from 0 to 7, not from 1 to 8. Now let's go to the prefabs folder and drag each of the bridge prefabs to one specific element in the array with one caveat, which is that the left and right corner segments have to be either the first 2 elements of the array or the last 2 elements. This is so that our random logic can be programmed easily later. I'm gonna make them the last 2. Let's save the changes and go back to the bridge spawner script in Visual Studio. Now let's create an enumeration structure that's gonna help us classify each segment as either left corner, straight, or right corner. Let's name it nType. Now we want to be able to take a prefab from the bridge prefabs array and pair it with its appropriate type under a single structure. To do that, we'll use a concept in object-oriented programming called classes, which allows us to encapsulate different data types, for example a game object and an enumeration, under a common structure. To create a new class in C#, just type the keyword class followed by the class name. We'll call ours capital S segments, because different segments are going to be spawned from its cloth, so to speak. This segment's class is going to have 2 public data members. The first is a game object member called segPrefab, and the other one is an nType enum called segType. And since the public members or variables, they can be accessed from outside the class, i.e. elsewhere in the script, like the start or the update function. Now these 2 variables are not initialized to anything, and there is a special way of initializing them using what's known in object-oriented programming as constructors. Let's start a new line. To call the constructor of a class in C#, just type public, and then the exact name of the class, followed by a pair of parentheses and curly brackets. So it's like a function of sort. Now let's pass in the class variables separated by a comma inside the parentheses. Now let's step into the body of this special function, i.e. the constructor, and type this dot segPrefab equals segPrefab. Terminate with a semicolon. Start a new line and type this dot segType equals segType, semicolon. So this block of code is basically specifying how the constructor of this class should be initialized. Now what's included in between the curly brackets is formally called the description of the class. Now let's create a variable from that class type and call it small s segment. This is formally called an instance of the big S segments class, or simply the small s segment object. Let's go to the start function and initialize the segment object using the constructor type segment equals new. And now let's call the constructor of the big S segments class. Let's initialize the segPrefab parameter to the regular eye-shaped bridge, which I have stored in the first element of the bridge prefabs array, as we have specified it in the inspector. And this is how we access an element of an array. We put brackets after the array's name and then the number of the element. The first element is indexed as 0. Now let's put a comma and initialize the segType parameter to straight. Now let's create a vector 3 that's going to be in charge of specifying the spawn coordinates for the prefabs in the scene. We'll call it spawnCoord, and we'll initialize it to 000. Now let's create a void function down here that's going to have the task of spawning different bridge segments in different directions in the scene. Let's name it spawn segments. First, let's create a local game object variable and set it equal to the seg prefab member of our segment object. Let's name our variable prefab to instantiate. And you can see that when we put a dot after the segment object, our public members show up, including the seg type and seg prefab. In object-oriented programming, this is called data encapsulation. It allows us to group multiple data, members, or variables under a single structure, which is very handy. We're actually going to use this variable to spawn whatever bridge segment prefab is stored in the seg prefab member to our scene. Also, let's create a local quaternion variable that's going to determine the rotation of the prefab that's yet to be instantiated in the scene. Let's call it prefab rotation and set it equal to the identity quaternion, which corresponds to no rotation. Now let's start a new line and write a simple if statement that's going to act as a sanity check for our script. If the prefab to instantiate is not null, meaning if this prefab to instantiate variable is not empty, then execute the following piece of code. And to instantiate or spawn a prefab at runtime, meaning as the game is playing, we use this instantiate function in Unity. And I've put an article that goes through instantiating prefabs at runtime in Unity from the Unity manual, so be sure to check it. So type instantiate, open parentheses. The first argument must be a game object variable that stores the prefab we want to spawn in our scene. For us, it's the prefab to instantiate variable. Then put a comma. Now the second argument is a vector 3 that tells this instantiate function where to place this prefab in the scene. We've already created the spawn coord variable, so put that in here. The final argument of this function, separated by a comma, is a quaternion that rotates the instantiated prefab in the scene. This is gonna be determined by our prefab rotation variable, so pass it in here. Now let's exit this if statement, and we're still in the body of the spawn segments function, and increment the z component by 6 units, which is the segment's length, so that when this function gets called again, the new prefab will be spawned at 0006, and if it gets called the third time, it will be spawned at 0012, and so on. Now let's go to the start function and write a simple for loop that's gonna call the spawn segments function 10 times. So this means that we're gonna spawn just 10 segments forward in the scene. And they are the same kind, which is the regular I-shaped segment. So start the counter I from 0, and as long as I is less than 10, execute this body of code, which is just the call for the spawn segment function. Then increment the loop counter by 1 after each iteration. You know what? Let's create an integer variable here and call it segsOnScreen and set it equal to 10. Let's go back to our for loop and put it in the condition by replacing the 10. This variable here indicates the visible segments that are ahead of the player on the screen. Let's save the changes to the script and go back to the editor and test our game. Let's remove this placeholder of a bridge from our game object hierarchy because we're gonna spawn our own bridge segments instead. Hit play. You can see that 10 regular I-shaped bridge segments have been spawned in our game ahead of the player, one after the other. And if we pause our game, we can see the spawned prefabs in the game object hierarchy. And there are exactly 10 of them. If we click on the first one, we can see in its inspector window that it has coordinates 000, and the next prefab game object has coordinates 006. And as we move to each adjacent segment, there will always be a 6-unit increment in the z forward direction. So our logic is working correctly. And if we stop our game, these 10 game objects get destroyed from our scene. This is because they are instantiated at runtime only. Now we want these forward segments to be randomly generated. So let's go back to the bridge spawner script and program the random logic. First, let's create an enumeration that's going to list the different directions our segments can be spawned at, and we'll call it in direction. Our segments can be spawned either east, north, or west. This enumeration is different from the one we've written in the player controller script, even though it has the same name. This one is specific to this script and hence only defined here. Now let's create a variable of type in direction and call it segCurrentDirection. Let's initialize it to north because we want our segments to be spawned north when the game starts. Also, this variable is going to determine the rotation of the prefab that's yet to be spawned in the scene. If it's north, then the prefab should have 0 rotation. If it's east, then the prefab should have a plus 90-degree rotation. And if the prefab is west, then it should have a minus 90-degree rotation. Let's create another in-direction variable called segNextDirection that we're going to use to change the direction of the segCurrentDirection variable if a left corner or a right corner segment is encountered. You can already see that it resembles the logic we programmed for our player to make him turn left and right. Now let's create a void function here and call it createSegments. This function is going to be in charge of generating random bridge segments and storing them in the seg prefab member of the segment object. Then we'll use the spawn segments function to spawn that randomly generated segment with the appropriate coordinates and rotation in the scene. So let's write a switch statement that's going to consider the logic for each direction, and we'll only consider the north direction case for now. We'll work on the east and west directions in the next tutorial. Okay, so our game plan for the random logic is to first select a segment type randomly from the n-type enumeration structure. So type segment dot seg type equals, and now we can assign an integer number to it from 0 to 2, with 0 being left corner, 1 being straight, and 2 being right corner, instead of typing it out explicitly. So really all we have to do is generate a random integer, and Unity has a designated method that does just that, called the random.range method. So type random.range, open parentheses. The first argument of this method is the lower bound integer, which in our case is 0. The second and final argument of this method is the upper bound integer number, which we want to be 3. Close parentheses and put a semicolon. So this line here says, randomly choose an integer from 0 to 2, which are 3 numbers in total, and assign it to the variable left of the equal sign with equal probability. So if we call this line 3 times, we can be sure that all 3 possibilities will show up one way or the other. Also, you can see the Visual Studio is giving us an error. This is because we need to typecast it as an n-type enumeration. So let's go after the equal sign and put n-type in between a pair of parentheses. Typecasting is a general programming concept that allows us to treat one variable type as if it were another, just like when an actor is being casted to play another character that's not themselves. So we're telling Visual Studio to understand this random.range value as an n-type enumeration and treat it as such just in this line. You can see that you're learning about all sorts of programming concepts in the process of developing this game. This is really a good way of learning programming because you could see how it's applied and how it can be helpful. Okay, let's go back to developing our random logic. Now because this seg type variable has many possible values, so it's not fixed, we want to write an if statement that goes over each possibility. So type if segment.segType is equivalent to straight, then set the seg prefab member of the segment object equal to. Now we want to select a random prefab that's not a corner from the bridge prefabs array. So type bridge prefabs, open brackets, and now we want to select a random element that's not a corner. So let's go back to the editor and check the elements in the bridge prefabs array from the inspector window of the bridge manager game object. And we can see that the straight segments are numbered from 0 to 5, so in total there are 5 elements. So let's go back to our bridge spawner script in Visual Studio and put the random range in the array index. So now if a straight type is randomly selected and assigned to the seg type member in the segment object in this line, then choose a random prefab from elements 0 to 4 in the bridge prefabs array and assign it to the seg prefab member of our segment object so that it can be later spawned to the scene from the spawn segments function. Also, let's consider the left and right corner cases. If the segment type happens to be a left corner, then assign the prefab stored in the 7th element of the array, which is the left corner prefab as I've put it. Likewise, for the right corner type, assign the prefab that's stored in the 6th element of the array. Okay, our random logic is done for the north direction. Now let's step into the spawn segments function and make some changes. We want to make our spawn logic more systematic and methodical so that it's easier to program for the other directions that are not north. So let's write a switch statement that's going to evaluate the segment's current direction and act accordingly. As with the create segments, we'll only consider the north direction in this tutorial. So if the segment type is straight, then the prefab rotation should be 0, and the segment's next direction should remain north, and the spawn coord variable is incremented in the z direction by the segment's length. You can see that I've written my if statement in one line, but actually every time there is a semicolon, Visual Studio treats what comes after it as a new line. And also let's remove the spawn coord increment from here because we have it in our if statement now. Moreover, we're incrementing the spawn coord z component before we instantiate the segment prefab. Therefore, we need to initialize it to -6 up here, so that when it starts at 0. Finally, we want to update the seg current direction by setting it equal to the seg next direction outside the switch statement. Now we're ready to test our newly programmed random behavior, but let's clean our code a bit more. Let's create a void function here called initialize segments. And let's cut and paste this code from the start function to the initialize segments function. And let's invoke the create segments function before we spawn the segments in the initialize segments function. Finally, let's call the initialize segments function in the start function. Also, let's comment out this line in the create segments function because we're not yet ready for the left and right corner types. So it's just gonna give us random straight segments. Save the changes and go back to the editor. Hit play. And you can see that we have many different types of segments spawned in the scene. If we stop and hit play again, we can see that now we have a different variation. So both our random and spawn logic seem to be working correctly. What we have to do now is generalize our spawn logic from just 10 segments to infinitely many segments. So let's go back to the bridge spawner script and implement such a logic. The only way to spawn infinitely many bridge segments is to have them triggered by the player's position in the scene. So as the player progresses through the segments, we want to spawn new ones in the scene and destroy the ones that the player had already run on. This means that we must grab a reference to the player's game object transform component. So let's go up here and declare a transform variable, and we'll call it player transform. And let's go to the start function and initialize it. Type player transform equals game object dot find game object with tag, open a pair of parentheses, a pair of quotation marks, big P player, then dot transform. Save the changes to the script and go back to the editor. Let's click on the player's game object from the hierarchy. Go to its inspector menu, go to tag. From the drop down menu, select player. Let's save the changes and go back to our script. Now this line here is gonna find the game object in our game with the tag player and get its transform component and assign it to the player transform variable. You could be wondering now whether we could have obtained the player's transform here in our script by making the player transform variable public and then dragging the player's game object onto it from the editor, just like we did with the camera logic script. And you would be right, we could have just as easily done that, but I wanted to introduce you to this concept of finding game objects in our game using tags, because we're gonna use it later for collision detection. What we need to do now is figure out a way of keeping track of the spawned segments in the scene so that we know which ones to keep, i.e. the ones that are ahead of the player, and which ones to destroy from the scene, i.e. the ones that the player had already run on. To achieve this, we're gonna use a special data structure or variable type called lists. A list is basically a dynamic array that shrinks and expands in size as the program or the game runs. So let's go up here and type list, then a pair of arrow brackets, and we want this list to store game objects, so put game object in between the arrow brackets. Let's name our list active segments, and we're calling it active segments because it's going to keep track of the spawned prefabs that are visible to the user at any given time in the scene. Now every C# list must be initialized using its default constructor, so let's set it equal to new list, a pair of arrow brackets, game object, then a pair of parentheses. Terminate the line with a semicolon. Now you might be wondering, couldn't we use an array to store the spawned prefabs? And the answer is no, because arrays have static size, meaning once we declare a size, say 8 elements, and hit play, the size remains fixed. We cannot grow or shrink the array while the game is running. However, we can do that with lists. Now let's go to the spawn segments and store the instantiated prefab in a local game object variable called spawned prefab. And let's typecast it as a game object so that we could add it to our active segments list because it's a list that stores game object. Now let's add it to our active segments list. So type active segments dot add, then open a pair of parentheses and add the game object we want to add. In our case, it's the game object stored in the spawned prefab, so let's put that in here. So once you spawn a prefab in the scene, add it to the active segments list. Now let's create a void function that's going to trigger the spawning of the segments according to the player's position in the scene. We'll call our function player trigger and invoke it in the update function. Let's go back to the player trigger function and create a local game object variable called go or go and set it equal to the 0th element of the active segments list. Now let's write an if statement that's going to check if the distance between the player's current position in the game and the bridge that's stored in the 0th element of the active segments list is bigger than some threshold that we will be deciding. To measure the distance, we'll use a method of the vector3 class called distance. This method takes two float arguments, a and b for example, and then outputs the distance between them as a float. So let's type vector3.distance, open a pair of parentheses. The first argument is player transform.position, comma. The second argument is the furthest spawned bridge behind the player in the scene, which we stored in our go variable. So type go.transform.position is greater than. So if the distance between these two game objects in the scene is greater than the length of two bridge segments, so let's put 12, then we want to generate a random segment and then spawn it in the scene. Now the last thing we need to do is destroy the bridge segment that's 12 units behind the player from our scene, and then remove it from the active segments list. And that bridge segment is the one that's stored in the 0th element of the active segments list. So let's invoke a function here called remove segments and create it up here. Type destroy then open a pair of parentheses. So let's put the game object that's stored in the 0th element of our active segments list for it to be destroyed. Then let's remove it from the list using the remove@. method. The reason we need to destroy and remove the segments once the player has run past them is because we'll get an out of memory exception if we don't do that. Our computer or phone has a finite amount of memory to run the game. So if we keep creating and spawning segments and loading them onto the memory, then at some point we'll run out of memory, so we must remove them. Let's read the code written in the player trigger function once more. If the player is 12 units ahead of this bridge segment, i.e. he had run past it and yet another bridge segment, then create a random segment and then spawn it to our scene ahead of the player. Finally, destroy the segments that's 12 units behind the player and remove it from the active segments list. So now when the game starts, this initialize segments function is called and it spawns as many segments as segs on screen and then adds them to the active segments list. Let's remove the create segments function call from here because we want our first few segments to always be regular eye-shaped bridge and not some random variety. From then on, we wait for the player to cross 2 segments, then randomly generate a new one and then spawn it to the scene. Finally, we delete and destroy the segment that's 12 units behind the player. This means that this active segments list has as many elements, i.e. prefabs, as there are segs on screen. This is because once the segments are initialized here, every element that's removed from the beginning of the list gets compensated at the end of the list with an addition of a new game object. And let's actually make it 5 because 10 is just too much, especially for mobile phones. Now before we test our newly coded behavior, I want to make sure that you understand what's happening in real time as the game runs. So I've created this interactive diagram that should help us understand what's really happening. Here we have 5 segments that have been randomly generated, spawned, and then added to our dynamic list, which is like our active segments list. As the player crosses 2 segments, the player trigger function gets activated and generates a random segment using the create segments function. That's why the question mark has disappeared because we now know the segment. Then it spawns that segment using the spawn segments function and then adds it to the dynamic list also using the spawn segments function. Then the player trigger function calls the remove segments function and destroy the bridge segment that's 12 units behind the player, which is the first element of the list indexed as 0. Finally, the remove segments function removes that destroyed game object or segment from our dynamic list. Then the process repeats all over again. Let's go back to the editor and hit play. We can see that the first 5 segments are regular eye-shaped segment. Then as we cross the second segment, a new random segment is spawned ahead of the player and the furthest segment behind him is destroyed. So it looks like we've implemented the spawning logic flawlessly. I'm surprised we got it right in one go. There's just one thing that we could optionally fix, which is that we want the spawned prefabs to be children of the bridge manager game object, like so. So let's go back to the bridge spawner script and add a new line here in the spawn segments function. Type spawned prefab.transform.parent equals this.transform. So set the parent of the spawned prefab to be this game object that this script is attached to, which is the bridge manager game object. And I think that we may have made a mistake here. This needs to be 6. Now let's save the changes and go back to the editor. Hit play. Now if we pause our game, we can see that the instantiated prefabs are children of the bridge manager game object, which is much neater. Okay, this marks the end of this tutorial. Now our game can finally be called an endless runner game. This is perhaps our longest tutorial, though it's not terribly long. And I think we've covered a lot of topics in a little over 20 minutes. And I must say, I really enjoyed making it. In the next tutorial, we're gonna generalize our logic to the east and west direction. Thank you.